Good afternoon, everyone. Today I'm going to present our latest work on automated deep learning based post-operative segmentation on brain tumor. Glioblastoma is the most aggressive and fast-growing malignant brain tumor in adults. The average length of survival is 12 to 15 months. The initial treatment involves the removing the tumor by surgery, and then it's followed by the radiation therapy and chemotherapy. So there is an infiltrating tumor surrounding the glioblastoma. So there is only a maximum possible resection have been done. After that, for the follow-up therapy, we need to manually delineate the specific region of interest for the treatment. So the manual delineation is labor intensive and prone to inter and intra and observer variabilities. So for this high-grade gliomas, especially for grade 3 and 4, the gross tumor volume is defined as the surgical cavity where the tumor was resected, and with the residual enhancing tumor around that surgical cavity on the post-operative T1 post-contrast images. So developing a robust automated segmentation tool for this GTV that will evaluate, help you evaluate the disease progression and also the follow-up treatment. There are several automated brain tumor segmentation models were developed for pre-operative glioma patients from the public data set like BRADS. But if you consider the post-operative cases, there are like very much less work was done already. And also we were not able to do the transfer learning from the pre-operative, post-operative segmentation models, because this is in the post-operative images, there will be a swelling and bleeding from the resection, from the surgical resection. So we aim to develop a segmentation model for especially focus on this post-operative images. For that, we acquired like 82 studies with high-grade glioma from our institution, collected from the 23 patients from the longitudinal study. Each data set will have 4 images, a T1 native and T1 post-contrast and T2 and T2 flared. And the annotations for GTV, that's the manual ground truth, were created on T1 post-contrast images. So for the pre-processing, we followed the regular method with the image registration with the ants and the brain extraction, the skull stripping. Also we standardize all the images for the same voxel spacing and the resolution. So for the architecture, we use the 3D pocket unit, which is like a regular unit, but the difference is that the number of feature maps from the encoder and the decoder part will remain constant, regardless the spatial resolution is reduces with the which reduce the total number of learnable parameters, and this reduces the time taken for the model training. So initially we trained like 8 baseline models with different input sets. From all 4 inputs we considered to the one single input, and we compared the dice and dice scores and the Hausdorff values. Here we learned that according to the input we have fed to the model, the dice accuracy is different for each case. So we tend to we compared the performance of the baseline models by considering like the cases were poorly performed, like poor segmented with the all 4 inputs fed to the network with like under 0.6 dice score. The image shows the first one is the model trained with like all 4 input. The last one is with only the post contrast image. You can see here how the segmentation accuracies vary with the model inputs. And this is also supported by the Hausdorff. So we learned that to have like accurate perfect segmentation, when combining the individual models we train, from that we can preserve the modality specific information we fed to the model training, and which may increase the segmentation accuracy. So we also for that we tried the ensemble modeling first. For this, like we took the 2 base models we have trained and combined the softmax output of them and did the segmentation prediction from that. This shows a little bit of increase in the die-scores compared to the base models. To even more improve the segmentation accuracy, we propose the double unit model, in which we have like 2 units. Both are pocket units. Here you can see that it's like every channel is having a similar value, but still the image dimension will be reduced in each step. So with this approach, we were able to concatenate the output of the 2 units together, and then just before the point-wise convolution operation. So based on the model input, we trained like 9 models from all 4 modalities used together in one for a training to like 2 modalities for a single channel. This shows the significant improvement in the segmentation accuracy compared to the base models or the ensemble models. We got like a highest die-score of 0.85 and cutoff with 4.1. So this graph shows the false positive and false negative errors of the 4 best performing models. Here, the first one is the model trained with all 4 inputs. Then the last one is the double unit model. Here also we use all 4 inputs, but one unit got 3 modalities, and the second input got only 2 different model images. Here you can see there is a significant reduction in the false positive error as well, and then false negative error. So we went on and checked with the case-by-case study. So here you can see this one such example where the first one, from left to right, the ground truth of the model we have trained. The ground truth, you can see that pink contour shows the resection cavity along with the enhancing tumor, that's a GTV. And when we train the model with all 4 inputs, here you can see that model over segmented out with the flare intensity just under this resection cavity. So in the post-operative cases, in T2 and flare sequences, there will be a signal inhomogeneity because of the intensity patterns from like edema or ventricles. That can be over-segmented by the model when you train with all 4 inputs. But when you cut down the input, like we trained the base model only with the post-contrast image, that model gives a better segmentation accuracy, but still it underpredicted the GTV. It underpredicted the resection cavity especially. So when we use the double unit method, which we give the flare in the one unit and the T2 in the other unit combined with the T1C, that can eliminate this flare hyperintensity and gave the better segmentation accuracy like 0.81 in this particular case. This is the another case where with all 4 inputs, it gave the better segmentation accuracy, but with only one post-contrast image when we use for the training, that under-segmented the resection cavity. But this double unit model can give the better accuracy, which reduces the false negative and false positive error considerably. This is the one good case, like whichever the model is like is having a perfect resection cavity and with surrounded enhancing tumor, which can perfectly predicted by all other models. So the results shows that the model performance varies with the input sequence fed for the model training, as well the presence of the infiltrating tumors and also the edema in the post-operative scans of T2 and flare. They tend to reduce the segmentation accuracy. Our double unit approach improved the model efficiency by 7% compared to the base models and the conventional way of training of the model with all 4 inputs. Currently, we are testing this proposed architecture with multi-center data like of BRADS 2024 post-glioma data to increase to check our model generalizability and the heterogeneity. I'd like to thank my advisor, Dr. David and Dr. Chung, and their lab members for their help toward this study. Thank you.
Thank you. Any questions?
Yeah. So the question is, what is the advantage over double unit, and that attention unit? So for this, we didn't try the attention unit, but I did try the unit and the double unit. So the unit, we fed all inputs together. In the double unit, what we are trying to do is like we are giving separate inputs for each unit, and then we combine the output of the both unit. This way, we can preserve the modality-specific information from the training. That increases segmentation accuracy. That's what we say. So he's asking like why we are using the T1C twice. So this is a double unit, as I said, like there are two different units trained simultaneously. So we use the post-contrast T1 in both cases because that only we define the ground truth. So that is the so like even with only the post-contrast T1, we were able to predict like good segmentation accuracy for many cases. But like a few cases failed where there is a hyperintensity from T2 or flare. So we try to cut down that. So we add up the T2 or flare with the T1C and see how it worked for the segmentation accuracy.
Any other questions? I had a question. So for the double unit, I guess it has twice the number of parameters as the pocket unit that you were comparing to?
No, it's like a double unit. Literally, it's 2 units together. So it's still as a pocket unit. But architecturally, it's a pocket unit. But pocket units like one single unit. Here, you use like 2 different units, and then we combining the output.
Right. So did you control for the number of overall parameters in the double unit versus the single pocket unit?
No, it's just act like 2 single units.
Right. So I guess my question is, if you had doubled the size of the single unit, how do you expect it would have?
It increases the training time. That's true. We are not like controlling the parameters to cut down the time or like training purpose. We just double everything.
Okay. And then another question based on your answer to the last question. So the clinician is only using the T1 post to do the segmentation. Is that right?
No, they do use all other images to comparison, but they do the segmentation on the T1C.
Got it. Okay, if there's no other questions, let's thank the speaker again. Thank you.